So, good evening once again. How are you? I hope you are doing good. So, here we are, our lecture number 1 on fluid mechanics, the new chapter that we have started today. Although we have done with mechanical properties of solid in the previous lecture, or you will know this chapter by the name of elasticity and viscosity. Okay. So, today we are going to have a fresh start with fluid mechanics, lecture number 1. Okay. So, as you have confirmed the screen is visible to you and I'm audible to you, we are going to wait for 1 minute more for the others to be joined, and then we will further proceed with our lecture. Okay, good. By the way, good evening. Good evening. How are you? I hope you are fine. Studies is going well. Okay. Have any kind of doubt in the previous lecture? Or like you have attended my lecture previously? Okay, okay. Yeah, that is why I'm thinking that this name appears first time for me in front of me. No problem. You are going to enjoy this session, huh? We are going to enjoy this. Okay. So I hope we should start the lecture. Others will be joining by their own time. Okay. So this is very important chapter. Okay. So please pay attention to this. Each and every concept of this chapter is just a, like I would say, the crucial and very important for the, like you say NEET and J for both. It is a very important chapter. So now, what is fluid? Firstly, this question arises to you. Okay, so what is our learning objective in this chapter? This chapter in NCRT, if you will see, the name of this chapter is, just a second. The name of this chapter is mechanical properties of fluids. Okay, if you see, go through your NCRT, this chapter is just after the mechanical properties of solid, and then after we have mechanical properties of fluid. So this is the name of this chapter in NCRT. But here we are going to deal with this as a name of fluid mechanics. Got it? Now, so what are learning objective in this? Firstly, we will learn about the pressure inside a fluid. Everything will be uh, kept very clear to you. Okay. Then we are going to learn about the buoyancy. What is buoyancy and Archimedes principle about the buoyancy. Then equation of continuity and Bernoulli equations, viscosity and surface tension. So these are the topics that we have to learn in this chapter. Not today, but in the entire chapter. Okay. So these are the topics. Now the very first topic we should start with, pressure inside a fluid. So what are the learning objective for today? I think Firstly, we will introduce that what is fluid, okay, and what is fluid pressure. Then Pascal's law and hydraulic machine. Everything will be crystal clear to you. Okay, these are the just name. Variation of pressure with depth in a fluid, and atmospheric pressure and gauge pressure. So we will apply our full potential to reach at this. Okay, got it? So be with me. I'm with you. Let's get started. So firstly, the very first question that arises in mind, that what is a fluid? Okay. From the childhood, we have a memory that fluid means a liquid, water. We just relate the fluid with water. No, I'm not saying that this is incorrect, but this is incomplete. Okay. A fluid is a substance which has a tendency to flow. Okay. Which has a tendency to flow from higher altitude to lower altitude, or you can say from high density to low density. Right? So if you go according to the definition of it, the fluid is a substance which can flow even under this a small application of force. Okay. You just disturbed it, it will start flowing. It has a tendency to flow. Okay. If you talk about anything like solid, if this is my hand, if I have a tendency to push it, it will go and then stop. Okay. But what if it is a fluid? I will just push it a little bit and it will continue its motion. When you have a glass of water and you just drop it, then what will happen? You have applied a certain type of force and it will start flowing on the floor. Your mama get angry on this, huh? So that is a different scenario. But what we are going to learn, we are going this that fluid has a tendency to flow. But now we cannot say that only liquid is a fluid, because we know that air can also flow. There is a flow of air, and air is nothing but a gas. So gases also have this tendency to flow. So in fluid, what we have covered, liquid plus solid. Sorry, liquid plus gas, because these are the two states of matter in which has a tendency to flow. Got it? So this is fluid. You can see in this animation also. This is the waterfall, a small waterfall, and this is a kind of gas. Okay. So both liquid and gas is known as fluid. Now, now what do you know by pressure? The very first topic that we are going to learn is the pressure. What is a pressure? If I talk about pressure, we said that every time that do not put more pressure on this, it will get break. Okay. Do not pressurize your children. Do not pressurize your uh, siblings and all. What does that exactly mean? What are they saying? If you see this video, if you see this, we are striking by this hammer on a nail that is going inside. So here we have two surfaces of contact. In the first case, we put this flat head just under the this hammer that we usually do. But what if I just inverted it? Would it be easier for you to push this inside? Tell me. In which case it is easier? Yes, exactly. So in this case, it will more penetrate, it will get more penetrate, but in this case, it will get less penetrate. And why it is so? Because the area of contact in this scenario of the nail is less. But if you talk about in this scenario, the area of contact is high. That is why the force that we exerted with the help of this hammer will get distributed only to this small area. Okay. but in this case it is distributed to a large area. That is why the effect of this force, we are applying the same force here, same force we have applied. But what happens that in this case, this force, let's say F, is distributed only this area, small area, very small area. But in this scenario, next case, the force is distributed to a very large area. That is why the effect of this force is less in this case, and effect of this force is more. And why it is so? We have applied the same force. Why it is not getting the same result? Because of the pressure. And that's why where the pressure came in the picture. So pressure is nothing but the force applied per unit area. Okay. So by the definition, you will see the pressure is nothing but force perpendicular to the surface applied on particular area. So by this formula, you can see if the in this case, if area is less, then this pressure will high, because if denominator will decrease, it will increase the entire value. For example, 10 by 5 and 10 by 2. We have kept the numerator constant and denominator we are decreasing. So in this case, we will get 8. In this case, we will get 2. So when the denominator decrease, it will increase the entire value of the fraction. So in this case, when area is less, the pressure will be high. But in the other case, when area is large, which means area increased, so it will decrease the entire value of pressure, means pressure will decrease. And that is why it is more easier to put this nail with this situation rather than this. Got it? I hope you are clear with this now. So whatever I have told you is written here. It is the normal force per unit area. If this is the area, this is the force vector. The pressure here is nothing but normal force per unit area, which means if I talk about this, like this is the force you have applied by an angle theta. So you will resolve this force into two direction. This is F sine theta, perpendicular downward, and this is F cos theta. You can simply see that this force cannot exert any kind of pressure on this surface. But this force, the perpendicular component of force, will definitely exert a force. Okay, about this area. So that is why we always take, if I talk about the pressure, so it will be F sine theta divided by area. Got it? So always take the perpendicular component of force, which is perpendicular to the surface. That is important. Okay. Yeah. Pressure is a scalar quantity. It has no direction. Unit of pressure is Newton per meter square or Pascal. Although we are going to see more unit of it later in the chapter. And the dimensional formula of it will be ml raised to power minus 1, t raised to power minus 2. Do you know how this formula came? You can answer it by thumbs up or thumbs down. Yeah, okay. Got it. So try to learn these formula. Very good. If you know this, it is very good for you. Now, another example, this is the kind of vegetable broccoli. You have must heard about it. So this is the knife. If you are going to cut any vegetable with the side which is not sharp, you will have to put more force to cut that vegetable. But from sharp end, it is very easier to cut the vegetable. Why it is so? Because sharp end, less area. If area is less, then pressure will increase. Got it? This is the only reason. In rail also, in railway track, these are the sleepers. These we put on the track. Let's say the video. Just a second. Okay. So we put the sleepers on the railway track, then we place the railway line on it so that the pressure will be equally distributed. Okay. Now, are you ready for the challenge? We are going to test your concept. How will you know about the pressure? Okay. So this is on your computer screen. Okay. So the question from you for you is why camel can easily walk in desert, but we cannot. Is this concept, is this in your answer? There is a kind of area if you are thinking about. If yes, then give it this. If no, then you can give this. So we are going to see the solution of it. This is your foot, and this is some kind of area you can calculate. This is particular area which is balanced by your vertical force, which is weight. So your weight is distributed only this area. But if you see a camel's foot, look at the size of it. Huh? So the area has increased in camel foot. Area of camel is greater than area of human. So that is why pressure is nothing but force upon area. If area increase, then pressure will decrease. So there is no much pressure on the feet of the camel. So it can easily walk without penetrating so much. But for us, if you talk about pressure exerted by human, this will be force, that is weight, divided by area of human, which is less. So if area of human is less, then pressure of human will also increase. So this will getting more penetrated in the sand. And that is why it is tough for us to walk in the desert. But you can see the camel not only walk, they will run on that. Okay. So a camel, which is much heavier, can easily walk on the sand because camel has a broad feet than the human. Okay. Got it? I hope you got this. This is not the very tough one. Now we talk about the density. You must have heard about that. If you will see, you take the example of honey and water. So if I talk about in which you can do this, you put the hand inside the liquid and get circulated it. So in which of the liquid it is easier for you to circulate this by your hand? Honey or water? Obviously water. Very good. Very good. You have answered it. Thank you. Why it is so? So one of the explanation that come in your mind is that honey is heavy than water. No? If you're thinking in this term, yeah, this is the viscosity. Also, why this viscosity? Viscosity came because of the density. Okay. We can say that instead of saying it viscosity, because most of the people will know have no idea about the viscosity. So instead of saying it viscosity, although you can say it to me, I can understand. But instead of saying the viscosity, you can say that honey is more denser than water. Got it? So now the question arises, what is this density? So density is nothing but density is defined as mass per unit volume. That how much mass is accumulated in particular in a specific volume. That is the density of that particular material. Got it? And it is a material property. Got it? And it is independent of mass. If you see by the expression, you will see, no, sir, it is directly dependent on mass. No. Suppose you have water. Just a second. This is a bucket you have. and there is a water inside it. Got it? Now water has some density, mass per unit volume. Suppose you put a partition in between. You have put a partition in between. So there is a liquid in this side also and this side. So will the density will change? Will the density will change by giving it? No. Although we have half the mass of it, half the mass is here, half of the mass is here. So that is why I'm saying that density is independent of mass. Okay. It is a intrinsic type of property. You will see it later. So density is defined as mass per unit volume. This is mass, this is volume. Scalar quantity, kilogram per meter cube is the unit, and also the dimension is this. Now, you can also see there is one of the density you will get to know. It is the relative density. So relative density is defined as if you measure the density with respect to some ideal fluid. Okay, and fluid is liquid or gas. So if you measure the density of any particular material with respect to some reference material, that density is defined as relative density. Suppose in your class there are 50 students. Okay, and some, don't suppose that you are in a 15 student. Suppose that your friend circle, about your friend circle, in your friend circle one of your friend is tall, one of your friend is short. So instead of knowing the exact value, you can say na ki I am tall from this girl and I am short from this girl. So that is the relative comparison we are doing. Same we are doing with the densities. So we are comparing the density of any particular fluid or any particular of material with respect to a reference material, and that reference material is water at 4 degrees Celsius for liquid and air at STP for gases. So it is the, I must write it here, and you also write it, that relative density is equals to density of a specific material, yeah, of a material, you can say, with respect to density of a reference material. Okay, got it? Now tell me, is the relative density is a scalar quantity? Yes, because it is a ratio of density, and density is a scalar quantity. The unit of relative density is kilogram per meter cube. Am I correct or not? Wrong. This time you are wrong, Harshili. And why it is so? Because it is the ratio of density to density. So how can it be a unit? Because if you talk about this numerically, it is, let's say, one of the material has a yeah, one of the material has a density like say 2 kilogram per meter cube, and water has a density, let's say, 1000 kilogram per meter cube. So this kilogram per meter cube also cancel out, na? So this is just a number and it is dimensionless. Got it? Now, example, try to solve this question. If the area of a dam, wall of a dam, is 20 meters square and the normal force of 1500 Newton is applied to the water by water on it, then calculate the pressure applied by the water on the wall. Are you able to calculate it? It is a very simple type question. So we are going to see the solution of it. Now, we know that pressure is nothing but the normal force per unit area. Hmm? So pressure, normal force is given to as 1500 Newton. Area you have given as 20 meter square. So please, yeah, very good. You have calculated the density. It's very good. You have calculated the density, but the pressure applied on the water has been asked. Okay, got it. Now you got it. So please take care about the dimensions, the unit in the question that is given to you. Sometime it will give you 20 centimeter square or millimeter square. So according to the situation, you have to change the unit also. Got it? Okay. Pressure is 75 Newton per meter square. I think you have disturbed with the unit, na? You have do the same calculation, but you are disturbed with the unit. So pressure has a unit of Newton per meter square, or you can say 1 Newton per meter square is equals to 1 Pascal. 1 P. Okay. What? No. Now we are. Oh, got it. So please correct it, na? Now you have corrected it, because unit will play a very vital and very important role. Now, now we are going to see the Pascal's law and hydraulic machine. Got it. Now, what is Pascal's law? Firstly, we will see that, and then the pressure. Okay. So, general idea of the pressure inside the liquid. So, we have take a jar, we have filled with it a liquid, and let's say water, and we have kept the three holes at different altitude or different depth. So you will see in general, this will cover this range, or the velocity of the higher point is less. This point has a less greater velocity than this point, and this point, the lowest point, has the highest velocity, which means if it is exerting out with a higher velocity, which means it has a higher acceleration. If it has a higher acceleration, which means the force applied here is very high. Okay. Or also you can also see why it is so, because at this point the amount of water that is exerting a pressure on it will be this, the larger one. If you talk about this reference line, only this amount of water is being supported by this point. And if you talk about this amount of water is supported by this. So it will have less force experience. It will have a greater than this one, but less than the lowest one. And the lowest one is the highest value of force experienced, or highest value of the pressure changed. So by this application, or by this demonstration, we would able to recall, we would able to conclude that when the depth in a liquid increases, it will somehow increase the pressure. Okay. So this pressure increases because liquid at lower depths has to support all of the water above it. This, at this point, if you talk about, it is supporting this much amount of volume of water. Got it? Now do not get confused with it. We are going to see the Pascal's law. Pascal's, the French scientist, the Blaise Pascal. So the statement of Pascal's law is that a change in pressure at any point in a confined incompressible fluid at rest. I am highlighting some important term. So a change in pressure at any point in a confined incompressible fluid at rest is transmitted undiminished to all the points in the fluid, which means if you have a confined place where you have stored a liquid, okay, and if you disturb it by one side, then this disturbance will go in the liquid at every place without losing its value, without any loss. Got it? Suppose I'm giving this example, although this is not relatable, but you can understand it. If you have a tub, bigger tub, and you just put a stone on that, this stone will disturb the geometry of this. It will penetrate in the water and get down, but it will disturb the water, and there are waves form on that. So it is similar to this. When we disturb the water at particular point, this disturbance will get distributed at all the points without any loss. That is the Pascal's law. So if we change the pressure of any particular side of an incompressible liquid, that pressure will be distributed undiminished to all the points in the fluid. Got it? So this is the definition. We are going to see it practically. What is this? Incompressible liquid means that liquid must not be compressed. Okay. In the previous lesson, in the mechanical properties of solid, I have told you that what is the compressibility and how does it affect, okay? And what is bulk modulus. So we have talked about all this. Now here, if you will see that this is a bottle. So this bottle is filled with the first. This bottle is filled with liquid that is non-compressible or incompressible, which cannot be compressed. Okay. Now, a 10 Newton force is applied a stopper with an area of 1 square meter. This has a particular area and we have applied a force on it of 10 Newton. Now this 10 Newton force will going to compress this a little bit. So this we have applied a pressure on that. And what the Pascal's law says? Pascal law said that a change in pressure at any point is confined incompressible fluid at rest is transmitted to undiminished to all the points in the fluid. So this pressure change that we have made by the application of this 10 Newton force will get distributed to all the points inside the, okay, got it? So if the bottom has an area of 2 meter square and each square meter is pushed by 10 Newton, then entire bottom will receive a 20 Newton push. Got it? Now, Pascal's also said that the pressure exerted at a point is same in all direction in a fluid at rest. So when the fluid is at rest, okay, fluid is not moving, acceleration is zero, velocity is also zero. And if you have exert some kind of pressure in it, you have applied a pressure in it, this pressure will distribute it to the entire liquid without any loss. But this is all that the Pascal has said. Now, got it? This is the direction of pressure you will see in any object inside the liquid. Now, we have considered a fluid element which is not exist, but we have assumed it. Okay, that is why it is a fluid element. It is ABC, this face, DEF, the opposite face of ABC. Just a second. Huh? A. So fluid element we have taken. This is the fluid element A, B, C, and D, E, F. So we are going to see that what are the forces that has to be exerted on the faces of it. So we know that the pressure exerted by the fluid is perpendicular to the surface, is always normal to the surface, because in pressure we already takes the pressure is defined as force that is acting normal to the surface per unit area. Okay, am I visible now? Yeah. So we know that the in pressure we take the perpendicular component of it. Now the force on this surface will acting in this direction, or must say the pressure in this surface it is acting in this direction perpendicular to the surface, and in the bottom side it is acting in like this direction. Clear? So we are going to see the variation of pressure or the expression of pressure for each of the surface. Okay. Now if you take, this is the force at B, FB, this is force FC which is acting on this surface, and this is the force FA which is acting on the downward surface. Got it? Now we will resolve this component if this angle is theta, so this angle must be theta. So we have resolved this component of force FB in two direction, FB sine theta and FB cos theta. This is the inclined surface that we have, this is the force exerted, and this is the angle theta. Okay, so we have assumed that with respect to x-axis and y-axis, this angle is also theta. You can say if this is theta, if you extend it here, this will be the normal perpendicular. If it is theta, this is 90 minus theta. Okay, so we can resolve it into two direction, which is FB sine of theta, and this is FB cos of theta. This angle would be theta. Note it, this is FB. Okay, clear? So horizontal direction में component we have FC is equals to FB sin theta. This FC we can relate it, okay, because fluid is at rest, so there is no acceleration due to these forces. So these, the net external force on the system must be zero. That is why this FC here in the horizontal direction must equate this FB sin theta. That is why we have written FC is equals to FB sin theta, and the perpendicular component must equate this FA. So FA is equals to FB cos of theta. Okay. Now I think it is clear from here. Clear? It is clear. Now we have taken particular areas. Let me rough all this. We have taken areas. Let the area of this inclined surface is AB. This surface is AC on which FC is acting, and this is for AA, for on which the force FAA is acting. Okay. So AC, similarly we can say AC is nothing but, if you resolve the AB, this angle is theta, this particular area is inclined at an angle theta, this is AB. So if you are able to resolve this, it will be AB cos of theta, and the perpendicular area will be AB sin theta. This horizontal area will equate this, and this is equals to AA. ठीक है. So that is why AA is equals to AB cos of theta and AC is equals to AB sin of theta. Now we are going to calculate the pressure on it. Pressure will be nothing but force upon area. If you talk about this surface, surface AB, so it will be force of FB divided by area of B is equals to force on FA. If you see that pressure at A will be FA divided by area of A, okay? And pressure at C will be F at C divided by area of C. So if you put the value of FC, FA and AC, AA, then you will have, if you talk about this FC also, FC is nothing but FB sine theta. And if you talk about this value AC, which is nothing but AB sine theta. So sine theta will cancel out. This will equals to FB over AB. And similar expression come for FA, sorry, PA. So we can say that pressure at A is equals to pressure at B is equals to pressure at C. Got it? So this is we are going to, this is known as the Pascal's law. So any variation given on this surface will equally distributed to this surface and this surface. We have seen it by an example. Got it? That is why the distribution of pressure is uniform. But one of the main condition is, two condition we are given. First, that the liquid must be incompressible, and second, that the liquid or that fluid must be at rest. Now, this is also termed as the hydrostatic paradox. This situation, it is hydrostatic paradox. Now, in this situation, what we have did, we have three different types of geometry. We have filled the water inside them at the same level. So you can see that the liquid, weight of the liquid at C is not equals to weight of the liquid at A and weight of the liquid at B, because the geometry is different. So they are holding the different amount of liquid, you know? Or instead of weight, you will write as amount. Amount of water in C is not equals to amount of water in B and is not equals to amount of water in A. Simple. But in this line, at the same level, if you measure the pressure of it, if you measure the pressure of it, the pressure would be same. And that is why it is a paradox of it. Because we know that in pressure, it is force perpendicular per unit area. And this force perpendicular is came from the weight. So we can say that weight upon weight is the essential factor, which means more weight, more pressure. But by this definition or by this observation, this is practically observed. At the same level, the pressure is same. So this is controversing their own statement. So that is why it is a paradox. So at the same level, the pressure would be same. So whatever be the geometry, so it is independent of the shape of the liquid. Okay, got it? Shape of the container. So the pressure variation is independent of the shape of container. Got it? I hope you got this. Now, hydraulic machines. Hydraulic machines are the machine that works on the principle of Pascal's law, and also their the working unit in them is fluid. Okay? Like if you say the petrol engine, petrol engine mein, what is the working unit? Working unit is petrol, because petrol burnt, it will generate the heat, exert the pressure on the piston, and it will get work. The work will be done there. But in hydraulic machine, this working fluid is this working element is fluid, either it is liquid or gas. Got it? So what we have done, suppose you can also make a hydraulic machine at your home, a simple one. Suppose this is a kind of uh, container. Both the ends are open, but they are different area and different shape. Okay. So I have filled a incompressible liquid in this container. Okay. And at the lower end, I have applied a force. This is a piston. So I have pushed it down. Okay. I have pushed it down. So this will go down. The piston will go down. So according to Pascal's law, what will happen? This variation of pressure, if the fluid is incompressible and at rest, this variation of pressure, this change of pressure will get distributed to the entire liquid, to the complete fluid, without any loss, without diminishing. So this change will lift this heavier part, will lift this heavier object. Got it? And this is the hydraulic machine. Now, the concept I have gave you, we will see the detailed explanation of it. So these are machines which works on the principle of Pascal's law. This is the kind of hydraulic machine. This is also, I think you have seen this in movies. These machines are very much used to lift up the car when the tire got punctured. So one of the machine that we use. Okay. And this also, the brakes, hydraulic brakes, na? You have seen. These are also termed as the disc brake. We usually see them. Have you seen them in a motorbike? And nowadays these are coming in cycles also. No, you haven't seen them. In the front wheel of any vehicle, you will see any motorbike of nowadays. You will see the example of Pulsar, Discover. So in that you will find it. Okay, it's okay if you have not seen it. Try to observe it from today. Okay. Now, this is a kind of scenario we have. In this is a hydraulic lift. So if I push this piston down, this liquid is incompressible. This liquid is incompressible. So what will happen? The way change in pressure will go undiminished to the other end, and it will exert the same pressure on it. Sorry, same force on this piston, but because of the area, the pressure would be different, and it will be able to lift this heavy object, this car, with the help of this little piston. So that is the very demanding and very important application of Pascal's law, and very useful also. So hydraulic lift is also the same concept. A small force is applied as input and a large force is received at the output. Now, we know that original force will be pressure P1 into A1, because in this side, if I calculate the pressure, the force applied is F1, area is A1. So force applied, you can say it is P1 into A1. But on this side, the pressure will be P2 because area has been changed. So it is F2 into divided by A2. So force will be P2 into A2. Now, So here, but what the Pascal's law said? Pascal's law said that if you change the pressure of one side, let's say the change in pressure is delta P. So this delta P will go to this side also without loss, which means there is no sufficient change in pressure on both sides. Okay, that is why the Pascal's principle said that P1 is equals to P2. Okay, now if you put this in the formula, P1 is equals to P2, you put the value of P1, so you will have this, which means the force on the other side will be 10 times greater than the this force that we have applied. That is why we are able to lift this force, lift this weight, heavy weight. Got it? Ready for the challenge? Okay. Now, very this is a common question that arises in the student minds, that pressure is the ratio of force and area. Force is a vector quantity and area is also a vector quantity, if you will see in the upcoming chapters. So why it is so that hydrostatic pressure we have taken as the scalar quantity? Why it is so? Because it is happened because the hydrostatic pressure is applied uniformly in all direction. In all direction. That is why the Pascal's law hold good. Okay. So when a force is applied at any point, the hydrostatic pressure is transmitted equally in all direction and not just in one particular direction. And that is why we cannot take the pressure as the vector quantity, because for vector it has to be in a particular specific direction. Got it? So that is why we have taken pressure as a scalar quantity. And also the pressure will not follow the vector laws of addition, subtraction, multiplication. So for any quantity to be vector, the vector laws must be followed. Similar goes for current. Current will also has a direction. It move opposite to the flow of electron, but it is also a scalar quantity. Same, because it is not follow the vector's law of addition, subtraction or not. So that is why we cannot consider it to be a vector quantity. And same explanation you can give for hydrostatic pressure. Okay. So thank you so much for being attentive. If you have any kind of doubt, you can ask. Otherwise, the lecture is being over. Thank you so much for being attentive. Have a good day. And if you have a doubt, you can ask. Thank you so much, Harshali. Thank you so much for being attentive. Nice day. It's good for me that you don't have any doubt.